Okay, welcome to this lesson on quadratic word problems. Now, the good thing about most quadratic word problems is that the equation is given to you. So you just have to figure out exactly what you're being asked to find and then use skills you already have to solve the problem. Now, here are the skills that you already have. You know how to graph quadratic functions. You know how to evaluate them at a certain point using functional notation. You definitely know how to find the vertex. And you know how to find the x and y intercepts if you have a graph or using a calculator. So what you need to learn is this last step. You need to just determine what type of word problem you're dealing with. Now let's explore that a little bit more. There are basically three kinds of word problems for quadratics. The first are minimum-maximum problems, min-max problems. The second type are x-intercept problems, or sometimes we call x-intercepts roots or zeros. And the third type is evaluate the function type problems. Please pause now and make sure that you have these three kinds of problems spelled out in your notes. Now first we'll just look at an example of a min-max problems. These are problems where we want to find the minimum or maximum. Now you know that always occurs at the vertex. Okay, so we have seen that the vertex is in general form is usually given by the formula negative b divided by 2a, and the y value is the function evaluated at the point negative b divided by 2a. The y value of the vertex is either the minimum value or the maximum value. Y is a minimum value when a is greater than 0, and y is a maximum value when a is less than 0. So keeping all that in mind, let's take a look at an example. Pause now and make sure that you have all of these points in your notes. So let's look at this problem. Now this is very typical. You will probably, in most cases, be given an equation that looks like some sort of standard form quadratic, and in this case we have an equation that models the number of bacteria in food that has been refrigerated, and it's given by this function 20t squared minus 20t plus 120, where t is the temperature of the food in Celsius. Now the question we're asking is, what is the minimum number of bacteria found in the food? We are looking for a minimum. Therefore, this is a min-max problem. And we know that the minimum is always found at the vertex. Okay, so we're going to go ahead and use our true formula, our tried and true formula, negative b divided by 2a. Now in this case, b is negative 20 and a is positive 20. So we're going to use that formula, and we will determine that t is equal to 1/2. Next, we're going to find the y value of our vertex. Now we know that that is our minimum value. How do we do that? We're going to evaluate this function n of t when t is equal to 1/2. So I'm going to substitute 1/2 in every place I see t in the original function, and I will determine that when t is 1/2, n of t is equal to 1/15. Therefore, the answer to this question is the minimum number of bacteria found in this refrigerated food is 115. Pause now and make sure that you have this entire example, including the math, in your notes. Now the next kind of problem we want to look at are root problems, otherwise known as x-intercept problems, or we might call these problems where we need to find the zeros. Now they're problems where we want to find the roots of the quadratic functions And we know the roots are at the x-intercepts. Now, how do you find the x-intercepts? Well, since we know that they always occur when y is 0, then we can take a look at a graph. If we have a graph, a lot of times in these problems, we will give you a graph. But if you don't have a graph, then you can use your calculator or paper and pencil and graph the function. And once you have the graph, then you should be able to identify the x-intercepts just by eyeballing it, because you know at that point y is 0. So let's look at an example of a root word problem or an x-intercept word problem. In this problem, a duck dives underwater and we model its path with this quadratic function. Y is equal to 2x squared minus 4x. Y is the position of the duck, or how deep the duck is. You can look at it that way. And x represents the amount of time the duck was in the water. So I want to know, how long was the duck underwater? So I'm going to graph this function. Here's what a graph looks like. Now I didn't cut this graph off. I left it with its values above the x-axis, but the way I'm interpreting this particular graph is that the x-axis is the water, and anything below the x-axis represents the duck being in the water. Alright, so I'm going to identify the x-intercepts because x is time, and if I want to know how long the duck was in the water, then I have to know something about that x-intercept that is at the far right-hand part of the graph. And I see that the first x-intercept is 0, 0. Now I'm going to interpret that to mean that the duck starts the dive at 0 seconds, and at that point in time, he had a depth of 0. The duck ends the dive at 2 seconds, and he has a depth of 0. So then the answer to my question is, the duck was in the water a total of 2 seconds. So that's an example of a problem where we might want to find the x-intercepts, and that's how we will answer our word problem. Please pause now and make sure that you have this entire example copied down, including any questions you might have. Now, last, we're going to look at a problem where we need to evaluate the function at a certain point. Now, we do that by substituting in whatever point we want in for x and evaluating the function. Now, let's take a look at what I mean when I say that, just to be clear. Way back in the first 6 weeks, we studied evaluating functions. So if I were given a function 3x squared minus 2x plus 12, and I asked you, what is f of 2? What I'm asking you is to evaluate this function when x is 2. Now I see here I have a typo, and what I really did was evaluate this function when x was 3, so bear with me. We're evaluating f of 3, not f of 2. And you see here all my math. I substitute 3 every place I see x. And then I just do the calculations to figure out what f of 3 is. So 3 squared is 9. And 2 times 3 is 6. So I have 3 times 9 minus 6 plus 12. That gives me 27 minus 6 plus 12. 27 minus 6 is 21. So I have 21 plus 12. And my final result is 33. And so f of 3 is equal to 33. Please pause now and copy down this example, taking care to note that it is f of 2. F of 3, not f of 2. Now, this is kind of a contrived problem that I made up, but here it is. I kicked the ball, and the path of the ball can be modeled by this little equation. Now, I have a pretty simple little quadratic here. It doesn't even have a y-intercept. Well, it does, but the y-intercept is at 0, 0. And if I graphed it, this graph would model the flight of the ball after I kicked it. Now the question is, where was this ball at 9 seconds? Well, in this equation, f of x represents the height of the ball, and x represents the time in seconds. So let me repeat that. F of x represents the height of the ball, in other words, how high it got. And the x-axis represents the time in seconds that the ball was in the air. And I want to know, where was this ball at 9 seconds? Well, I could just look at my graph and count off the seconds here. Here's 5 seconds, 6, 7, 8, 9, and then I could go look and see where it was, and it was right here, and it turns out that the ball was 9 feet in the air at 9 seconds. What a coincidence. So I could just graph it and then answer the question based on the graph. But sometimes the graphs are so big it's difficult to graph certain things or numbers that are on whole numbers. I might need to do this algebraically. If I do need to do that, I'm going to use function notation like this. Where was the ball in 9 seconds? Well, if I know that x is seconds, then everywhere I see x, I'm going to substitute 9. In other words, I'm going to evaluate this function at 9. So I see that f of 9 is equal to 1/3 times 9 squared plus 4 times 9. And after I do all this math calculation, I will come to the conclusion that f of 9 is equal to 9. Therefore, the ball was at 9 feet in the air at 9 seconds. So, pause now and make sure that you copy everything on this slide and this slide, and make sure that you write down any questions that you might have. I have given you some pretty simple examples. In class, we will practice examples that are more complex. We will go a little bit harder and a little bit harder until we get to the kinds of problems that you will be having on your exams and on your homework and future assignments. So please make sure that you write down any questions you have and come to class ready to work.